Now we will turn to the derivation of a mathematical model describing the interactions between predators and prey. We are going to derive a set of equations, a mathematical model called the Lotka-Volterra model. And just as a reference, you can consult these two textbooks for more details on this type of derivation. And when in the first steps of constructing a mathematical model, we have to make assumptions. And then we'll use some equations or some mathematical expressions that are consistent with these assumptions. These models bear their names because of the two individuals that work almost at the same time in developing this theory, even though they were working independently. One of them is Vito Volterra, and the other one is Lotka. This was in the early 1920s. So we're going to use some notation. Here we're interested on describing dynamics of populations, and we're interested on the population, the size of a population being described as a function of time. So we're going to use the letter x of t to denote the state variable for the size of the population of prey, and y of t will denote the population size of the population of predators. So to start the model, we make some standard assumptions. If it is assumed the prey have an unlimited food supply in such a way that the growth rate per capita of prey in the absence of predators would be constant. Okay, so what do we mean by this? The population size is x of t. The rate of change of population size would be dx dt, and the rate of change of population size scaled by the population size is the so-called per capita growth rate, the growth rate per individual in the population of prey in this case. So when we make the assumption that the prey have a food supply with no limits, in the absence of predators this would be constant, we are saying that this ratio of the derivative of the prey population size scaled by the prey population size equals a constant. In this case, we denote that constant with the letter lambda. We assume this constant is positive. So what we are saying is that the derivative of x, the rate of change of population size, equals lambda x, and where lambda is positive. This is perhaps one of the most fundamental differential equations. It's a linear differential equations you can solve exactly. In calculus jargon, this says that the derivative is a multiple of itself. The derivative of a function x is a multiple lambda, where lambda is a constant, is a multiple lambda of that function x. This is the signature of a very special function in mathematics called the exponential function. It has an exact solution that looks like this, and we know that for basically this is saying that when we make these assumptions of constant per capita growth rate, that this mathematically this is equivalent to assume exponential growth on the population of prey, that in the absence of predators, the population of prey has an unlimited food supply, and because of that food supply with no limits, then that population is destined to grow exponentially, right? So the other way of picturing the exponential growth is if we sketch the graph of x of t, so this would be t here on the horizontal axis, and x of t, this point here is what we call the initial condition, and this is a graph of this type of functions, an exponential growth. It's destined to growth because lambda, the parameter that denotes this constant per capita growth rate, is precisely the parameter of that exponential function. On the other hand, predators depend on prey. Prey are the food supply of the predators. So if we assume that prey is absent, we're going to assume that in the absence of prey, the predators would have nothing to eat and would be destined to be on decline. So in such case, would have a death rate that is constant, a per capita death rate that is constant. So what we're saying with this assumption is that the size of the population of predators, the rate of change on the population size of predators is scaled by the predator population size. So that's again this ratio of the derivative of the function divided by the function. We're saying that this ratio equals to a constant, but this in this case is a negative. It's a negative constant. So we assume that mu is positive and therefore minus mu is negative, right? So mathematically, this is very similar to the previous case. This ratio, dy dt divided by y, translates as the derivative of y equals minus mu y. Mathematically, this is still saying that the derivative of a function is still a multiple of the function. In the previous case, it was a positive multiple. In this case, a negative multiple. The exact solution of this equation takes this form, and now we can see that in a consistent feature, the parameter that denotes the constant per capita death rate is the parameter of this exponential function, right? And so the drawing here, similar to the drawing within the previous page, says that we have t on the horizontal axis, y on the vertical axis, and we have some initial condition here, and then this is a little sketch here of this function y of t. Okay, so in the absence of prey, the predators decline exponentially. That's basically one of the basic assumptions of this model. So those are the building blocks. Those are the basic assumptions, and now we are going to build on those assumptions. We're going to make some modifications. So the idea here is that predators need prey as their food supply. And in the basic assumption, we were considering that without food supply, they would be destined to exponential decay. So if there are prey, then that would have a positive impact on the population of predators. So we will modify the assumption that now in the presence of prey, we're going to assume that the per capita death rate changes from a negative constant, from minus mu, into a quantity that is a function of the size of prey. So there will be a change from negative mu into minus mu plus cx. In other words, this ratio, derivative of population size of predators divided by the predator population size, now this is equal to minus mu plus a constant times the size of the population of prey. So now we're going to assume that in the presence of predators, then the per capita growth rate of prey is going to change from a positive constant from lambda into a quantity that is also a function of the size of predators. So it changes from lambda to lambda minus by. In other words, this ratio, dx dt divided by x, is now equal to lambda minus by. So what we are contemplating are two equations. As we saw in the previous page, we are adjusting to the presence, right? We're writing expressions in the absence of one species and now adjusting an expression that makes sense in the presence of the species. So the derivative that denotes the rate of change in the population size of prey becomes dx dt equals x times lambda minus by. And for and if you multiply, you do a little extra step, then that gives us an expression for the rate of change of the population size of prey. And from the second expression, we obtain that dy dt equals lambda times quantity minus mu plus cx, and that gives us another expression. We multiply, we distribute here the y, gives us another expression for the rate of change on the population of predators. So in summary, we have two differential equations. These differential equations are coupled. Key terms here. There are some key terms. For example, this term b times xy and this term c times xy, those terms denote the interactions, right? So they denote the interactions between predator and prey. So the other terms are also important, and we will discuss them in more detail a little later. But one of the key signatures or footprints of this basic model for the interactions between predators and prey is this term, this xy term. This is in a context is also a term that is referred to the law of mass action in chemistry. That is the term that makes these equations nonlinear. This is a system of ordinary differential equations, and because of the product x times y, this system is nonlinear. Okay? Now, one of the things we can do with this mathematical model for predators and prey is to find numerical solutions. And what we're seeing here at the bottom is a simulation. This is a numerical solution that was computed, and this is computed using something that most of you all of you are familiar with. You can use the R package called LSODA. Okay, you use R and use that package LSODA for computing numerical solutions of differential equations. Here you have parameters lambda, b, mu, and c. You need values for those parameters. You need some values for the initial conditions, and then you can do, basically you can replicate this this graph. What this is telling us is that here we have in blue is the number of prey, so the solution let's remember that these are differential equations. The solution of the differential equation is a function of time. In this case, the state variable vector stores x of t and y of t. So when we compute a numerical solution, we will have a function of time. X of t is displayed here in blue. Y of t is the population of prey is x of t displayed as a solid blue curve, and the population of predator, y of t, is displayed as a dashed red curve. An interesting feature to observe is how there is a cyclic nature for the interaction and the dynamics, the temporal dynamics between these two species. For example, we can see that at the beginning, we have a pattern of repetition, right? So that's the idea of having this cyclic behavior. So we want to kind of zoom in into one of those intervals of time when there is established pattern and understand how that pattern repeats itself. You can see how the simulation starts at t equals 0. And if we follow the trend of the prey population, right? So we're looking here at t equals 0. The prey population, x of t, is at a very low level, and then it undergoes a sharp growth, right? It kind of peaks a little bit after here at a time, a little bit after t equals 2, and after that, then it goes on decline. So you can see that the pattern of the population of predator, it actually goes a sharp decline when there are very low levels of prey around, and it starts rising precisely at times in which there is great abundance of, right? So here where you can see this dash curve in a changing from a decline into a rising or growth is precisely at times in where there is a great abundance of food for them. The food supply is is in excess, right? And then at some point, the population of predator basically maxes out, reaches its maximum, the red dash curve, and then it undergoes a decline. And it undergoes a decline exactly at the time when prey is kind of sparse or scarce, right? And so then the cycle repeats, right? So the growth, the rise and fall of both of these populations is coupled, right? One population is going to increase up to a high level, and it will undergo a decline, and that will have a repercussion on the other population. So when we compute a numerical solution of the type we had in the previous slide, numerical solution of this type, we can display the numerical solution as a function of time. This is what we call a time plot. But remember here, for every time point, say, I don't know, they say number 2, at 2, x has this value and, y has this value here in red dash, and x has another value there that corresponds to t equals 2 on the blue curve. If you look at t equals 4, here's the value of x, here's the value of y. At t equals 6, here's the value of y, there's the value of x, and so on. So at each time step, there is a value x of t and y of t, right? So you could think, if I write here x of 2, y of 2, and then x at 4, y at 4, and then x at 6, y at 6. So you could see where this is going. We could have a table of x, y values, okay? And now what we would like to do is to have another visualization of the same numerical solution. So those x, y values, we can display those x, y values into a plot that has the state variable x of t on the horizontal axis and the other state variable on the vertical axis. And this plot is depicting each of those xy values into a plane that is called the phase plane, right? So this here, the fact that every pair is denoted with a little circle, the fact that this denotes a curve that is closed, meaning that, well, that's what this type of curve is called. This is called a closed curve. This is related to the fact that the time solutions have established oscillatory pattern. These are sustained oscillations, and because these are sustained oscillations, then when these solutions are displayed in the phase plane, then what we see is a closed curve, something that looks like a circle or an ellipse. It's a closed curve. Okay, so as I said, these type of numerical solutions are very straightforward to obtain using the command lsoda. This is part of the R package that is used to compute numerical solutions of differential equations. And this concludes our introduction to a model for the interaction between predators and prey.